Thomas.
No, it's I can do without a mic. All right. Dames en heren, ladies and gentlemen, geachte collega's, dear colleagues. So I hereby formally open this session and I welcome you all to the public defense of Soetkin Janssens. Maybe I want to first present the examination committee. So the two supervisors are Pim, Sanne, and Tomer Senna, who are here. And then two external members are Nathalie Degna from the University of Amsterdam, who is here, and the other one is Professor Sylvia Tonnen, but unfortunately she couldn't make it today. But the questions have been passed on to the supervisors. So you will give the questions. There's Dr. Pablo Marchand. Did I say it correctly? Marchand. From Leuven. Then there's Professor Janssens from Leuven and Professor Joris from Leuven, and myself, I'm also from Leuven. My name is Thomas van Riet. So Soetkin has presented to the faculty the PhD thesis on the topic of the search for massive single degenerate binaries in the Milky Way, in partial fulfillment of the requirements for obtaining the degree of PhD in science, astronomy and astrophysics. And Soetkin, Janssens shall now publicly defend her PhD thesis. Soetkin, you are invited to give a presentation of about 45 minutes about your work. Afterwards, the examination committee will ask questions and discuss the work with you. So I give you now the floor.
Thank you. Okay, so hello everyone. Is this sound fine? Okay, so hello everyone. Thank you for coming today. And indeed, I will today be publicly defending my PhD under the title of The Search for Single Degenerate Massive Binaries in the Milky Way. That's a whole lot of scientific words, but I will walk you through the title, and I'm going to go from the back to the front. First off, we start with the Milky Way. I think this one seems quite obvious. We will be studying objects in our own galaxy. Then we have the massive binaries. And if we say binaries, we need stars. So this image that you see on the left is an image of the sun taken by the Solar Dynamics Observatory from NASA. And it is the star closest to us. And what is the sun? It's basically a hot ball of gas. This gas is not a little bit of gas, it has a whole lot of mass, and so we have a lot of gravity that really pulls the gas together, giving it a nice spherical shape. What we have in the star is a certain structure. We have an envelope, which are the outer layers of the star, and then we have the core. And the core is very hot, dense, and we have nuclear reactions happening in here. So for example, we have 4 hydrogen atoms that we're burning into helium. And this reaction gives us a lot of energy. And for a large part of the star's lifetime, it will do this reaction, and hence it can actually, this energy gives us a bit of energy or internal pressure to counteract gravity. So the star is nicely balanced for at least most of its life. So the sun is actually what we call a low-mass star. And by definition, it is born with 1 solar mass. So every time you will see this kind of circle with a dot in it, I will be talking in solar units, because the sun, it's very nice, convenient for us. We want to scale everything to the sun instead of using 10 to the power 30 kilograms. And by definition, also, the sun has 1 solar luminosity. So that's how bright it is. Now, if we look at massive stars, they are much more heavy. They're born with at least 8 times the mass of the sun, and they can be at least 1,000 times as bright as the sun. So what I'm going to study is really the hottest, brightest, biggest stars in our universe. And these stars are very important because during their lifetimes, stars are not static, they evolve, and so they will really care for the chemical enrichment of the galaxy, of the universe, and impact star formation in their surroundings. So quite important. But what is the big difference between these stars? Why do we distinguish between the sun and massive stars? And I think, at least for my research, the important part is in the ending. the sun will become a white dwarf. Whereas massive stars, at the end of their lives, they will go a violent supernova, and hence they become neutron stars and black holes. So that's kind of the classical picture. And here you can see also I put some masses for these objects. And so we really believe that only the more massive stars really become black holes. And so you can see black holes are also a bit more massive than the neutron stars. And these two, neutron stars and black holes, are in this presentation referred to as compact objects. Then we, of course, were going for the binary. So what is a binary? It's basically two gravitationally bound stars that orbit around a common center of mass. And the time they do it, in which they do this, is the orbital period. The orbital period can really have a wide range. It can go from seconds, minutes, to months, and even thousands of years. So really a wide variety in binary periods. And one other aspect of binaries that I want you to get is the eccentricity. And this tells us how circular a binary is. On the left side, you can see a circular orbit, and this means we have an eccentricity of 0. On the right side, you have a very elliptical orbit, so this one has a high eccentricity. And then, actually, good for us, most massive stars are found in binaries. So that's why we study the massive binaries. And then we get these degenerate objects. And I'm not going to go into the details of what these exactly are, but you need to know that with this, I mean the neutron stars and the black holes, because we're looking for the massive ones. And the single degenerate massive binaries are then our OB plus neutron star or OB plus black hole binaries. So now that we know what they are, why should we care about them? Well, maybe you've heard about the detection of gravitational waves in the last decade was a major achievement in astronomy. And what we really observed is actually the merger of two compact objects, so the merger of two black holes or two neutron stars, for example. And this merger gives us ripples in space, as you can see here in the animation. And this is what we observed. And as we observed it, the question comes, how do they form? Well, I told you that these OB stars, these massive stars, they form black holes and neutron stars. So maybe if I have two of them, I can get a compact object binary and a gravitational wave merger. So the question is, how does this happen? And just to be clear, of course, we have observed our massive OB binaries and our gravitational wave mergers. So both exist. The only question is, how do we get there? And this will be, I will show you one example. There are multiple options, but this is one example. So we start off with the binary, and one thing about stars is that the more massive it is, the faster it will evolve. And just like humans do, at least in the beginning of their lives, stars like to grow as they evolve. And so this most massive star will start to grow, and at some point, something will happen, which mainly that the mass of the envelope of this star will get attracted to the other star, to the least massive star, the secondary star. And this is what we call mass transfer. Now remember, we had the envelope and the core. So what happens during mass transfer? Part or fully the envelope will get dumped onto the other star. And then we end up with what is called a helium star, which is basically the core of the star, or a very stripped star, very hot. And the other star, because we have transferred mass onto it, we gain some angular momentum and it will start to spin up. And this is what we call a BE star, a rapid rotator. We also observed some of these stripped stars. So they exist too, that's great. Then second, this stripped star will go supernova and leave behind our first black hole. So here we have a massive single degenerate binary. Then what happens is the remaining star will also start growing. It will start transferring mass onto this black hole. The black hole cannot immediately accrete it, so we will have a little disk forming, which gives us the X-rays, which we call an X-ray binary. We also observed some of those. Now what will happen is, instead of the envelope being fully transferred onto the black hole, the star will keep on growing, and hence we have what we call a common envelope phase in this case, which means that the envelope of the star now fully engulfs the black hole as well. And because of friction of the two objects in this envelope, when the envelope is expelled, we are left with a very short period binary of, in this case, a black hole and our stripped star. Stripped star will go supernova, and we have our second black hole. That is a possible idea that we have. And so here, this phase, the OB plus black hole phase, these are the massive single degenerate binaries, and in this case, they are quiescent. What does this mean? Well, we have the X-ray binaries, and we have those that do not emit X-rays. And these are the quiescent ones. These are the ones that I am interested in. However, we have very few observations of these, whereas predictions do tell us that about hundreds of these should be there in the Milky Way. And maybe we're not really finding them because there are a couple of uncertainties in this. Maybe this scenario is just not fully correct. And one of these questions is, how do black holes form? And the second one is, how do the interactions happen? And these two questions will basically be the main focus of my thesis. And so we will start off with part one, which is finding the OB plus black holes. So as I said, how do black holes form? We don't really know. If they form with a very large supernova, they might lose a lot of mass, and so if we expel a lot of mass, we might not be able to form a black hole anymore because we don't have enough mass, and we form a neutron star. Or, on the other hand, if you have a neutron star in a kick, you might just kick out the binary from the system and you don't have a binary at all. And so in order to solve this question, we really need these OB plus black hole binaries. So let's search for them. Now, this is not so easy because black holes or neutron stars, they're not really shining any light. So we need to find ways to look for them, and we mostly do that through binaries. So here I'll explain a little bit of common binary detection methods. The first off I already introduced was gravitational waves. However, as I said, merger of compact objects, so not really our single degenerate binaries. Second, we have X-rays. I also briefly mentioned in which phase we get them. And so X-rays are very nice to find compact objects because most normal stars do not shine bright in the X-rays. So if we find some X-ray binaries, it's a very neat way of saying there is probably a compact object in there. However, distinguishing or saying it is a black hole is more difficult. So compact objects, great. Black holes, less great. Next, we have spectroscopy. And spectroscopy means we're going to look in the spectrum. And the spectrum, what we do with stars is we basically shine the light through a prism and we get this nice rainbow. And at the top you see an example of a spectrum of the sun, or well, a sketch of the spectrum of the sun. And what you see is these black lines. These black lines are absorption lines. What does this mean? You have a lot of atoms in the envelope or the atmosphere of the star, and some of the light will actually be absorbed by our atom, and hence we can't see this light ray. So we get this relative decrease in photons at certain wavelengths, and this is why we get the black lines. Now, these are very important for us because these tell us which elements are present in the star, they tell us temperature and everything, so we can get a lot of information out of these. And what we want to do is watch a star move around in the spectrum. And this is based on the principle of the Doppler shift. So I'm pretty sure everyone has already heard when you have an ambulance coming towards you and going away from you, the frequency and the sound change. Light does exactly the same thing. When a star moves away from us, everything will seem more stretched, longer wavelengths, and it will appear redder. On the other hand, if it moves towards us, you will get a decrease in wavelength and it will appear bluer. And we will use this principle, as you see in the animation, for a binary. Because in a binary, stars are constantly moving away of us, towards us, away from us, towards us. And so you get, as you can see here, really this shift in the A and B component. And this is how we can see binaries. Of course, if you want to detect a compact object, we want to see one of the stars move around nothing. So you imagine you have no B component. That's how we see it in a spectrum. Finally, there is one other technique, which is astrometry. This means we're basically looking at the motion of stars on the sky, because stars do not all move in the same way. And there are a couple of components that add up to the astrometric motion. And the first one is a parallax motion. If we observe a star, for example, in January, the Earth will have moved 6 months by the time we would observe it again in June, and so the stars will have an apparent motion on the sky, which will look circular or elliptical, just because of the motion of the Earth around the Sun. Second, we have the proper motion, which is due to the motion of the star in the Milky Way. This will appear more or less as a straight line. And if you combine both of these, you get a single star. You get a nice spiral structure on the sky. However, if you add to that a binary, a star moving on its own center of mass, you get this deviation from the nice binary, as you can see here. So these are the 4 techniques that are at least very relevant for my thesis. So now the question is, what did we find so far? And I'll tell you, most of the ones we found so far are from spectroscopy. And I don't expect you to be able to read all of the titles on this slide. This is just an overview or an idea to give you of the previous reports of quiescent black holes of the last, let's say, 5 years. Now, as it turns out, a lot of these systems have been followed up by other research teams, and unfortunately for us, a lot of them appear to not have a black hole in them, about half. On top of that, most of these black holes are found around low-mass stars, so not really about the massive stars that we are looking for. So the question we have is really, why are we not finding them? And as I said, maybe this is because of the black hole formation. We don't know it. Maybe the kick is so strong that we just kick them all out of the system and there are no massive binaries anymore with black holes. Maybe the supernovae are too violent. We don't get a black hole either. But there is another thing, and maybe our methods are just not ideal for the detection of OB plus black holes. And this is because it's easy to confuse certain things with a black hole in spectroscopy. And from left to right, we first start with a low-mass star. As I said, massive stars are thousands times brighter than the sun, so our massive star will just fully outshine a low-mass star in the spectrum. Second, the stripped star, this helium core, very hot object, which means that it shines very bright in the ultraviolet, but most of our spectroscopy is done in the optical, and so in the optical it will appear very dark, or barely visible. And then last, we have a rapid rotator, which means if you have a rapid rotation, you kind of start getting away from, you get a blade. And in the spectrum, you see this as well, and you see spectral lines that become very broad and sometimes very hard to detect. So, in this thesis, I explored a new method, which is Gaia. What is Gaia? So Gaia is a space telescope that is in orbit or with the Earth around the Sun, and it has observed almost 2 billion stars. What does it do? It basically just takes pictures or images of all the stars, and it measures positions for these stars. And with all these positions, it basically traces the astrometric motion that I talked about. Remember? This motion. So, and as I said, we can see the difference between a single and a binary star on the sky. So, Gaia can do this too. But we want to go even further, because we want to find these OB plus black hole binaries. And in order to see whether we can do this or not, it's important to take into account that Gaia, for us, does not see both stars. What it sees is the photocenter motion, which is very similar to the center of mass, but then for light. So let's take a look at the motion of the photocenter. Here I have 2 binaries. The top one is a star plus a black hole, and the bottom one is 2 stars. And if I show you the photocenter motion, you can see that when we have a black hole, there is only one light source, so the photocenter is located at the position of the star. However, at the bottom, we have 2 light sources, so the photocenter will always be located somewhere in between the center of mass and the position of the brightest star. So the motion of a non-black hole binary will be smaller than that of one that contains a black hole. And it's exactly on this principle that we will search for these OB plus black hole binaries. So, of course, the question is, it's very nice that this could work, but how would we find a couple of these black holes in a catalog of tens of thousands of stars in Gaia? It's really finding a couple of needles in a haystack. And for this, we will use what is called the astrometric mass ratio function. And that's a whole mouthful, so I will refer to this as the AMRF. And the AMRF basically says us, or we calculate what is the maximum photocenter motion we can get for a certain kind of system, and then we just compare it to what we observe. And for this, we have theoretical curves. So on the y-axis, you have just the value of the AMRF, and on the x-axis, you have the mass ratio, which is the mass of the least luminous star divided by that of the most luminous star. And it is, of course, dependent on the mass ratio, because depending on the masses of your stars, you have different lights coming from the star, and so your photocenter will shift, and hence your AMRF will have different values. So let's take a look at what are the maximum motions we expect for given systems. And the easiest one is the single degenerate binary. And as I said, this is the maximum motion, so there can be nothing on the left of that diagram, of this curve. Then we have the binaries, these unevolved massive binaries, and as I said, they have a lower photocenter motion, so their AMRF values are lower than those of single degenerate binaries. And then what we also have to take into account is some triples, so just 3 stars that are gravitationally bound, and just because of how these light ratios affect each other, the photocenter motion is a little bit larger than that of normal binaries. So if we would have a data point at a mass ratio of 1 and an AMRF of 0.1, we can clearly see it is above the binary curve, so it cannot be a normal binary. However, in reality, it's not so easy to know this mass ratio, and it can basically be anywhere. So we want to find a way around this, and we divide the diagram into 3 parts. First up are the class 3 systems. This is everything above the maximum of this triple curve, so it can't be a normal binary, it can't be a triple, so it must be our single degenerate binary. Second is class 2. This is in between the maximum of the binary and of the triple curve. This will be a combination of triples and OB plus black hole binaries. And then lastly, we have class 1, which basically can be anything. And so, of course, in this thesis, I want to classify binaries or systems as OB plus black holes, so class 3. But does it work? So for this, we did some simulations. And so we first simulate a population of our single degenerate massive binaries, of our OB plus black holes. And the first barrier they need to pass is, can Gaia see it as a binary? Can Gaia detect the photocenter motion? Maybe some systems will not pass through. But then the second barrier, of course, is, will we detect it as class 3 with the AMRF? And as it turns out, we find that about 70% of our whole population, of simulated population, can be detected as an OB plus black hole binary. Now, in terms of numbers, this would result in about 100 of these systems. And this would be incredible, because we would increase the currently known sample by a factor of 25 or way more. And so for the first time, we would really have a population of these systems that we can actually fully analyze and start understanding, instead of just this handful. So this really shows us, or I kind of told that we're interested in how do they form, and we need them, but how can we see exactly how they form? So in order to do this, we simulated also a little bit of different black hole formation scenarios. Some of these simulations will have a very powerful supernova, a lot of mass loss, and a strong kick. Other ones will have a very little mass loss, low kicks. And so we did a couple of experiments with this. And what we can find is these kind of things. So here I show you the eccentricity distribution. Remember how circular is our system? This is the fraction of systems. This just is, the higher it is, the more systems we expect to find here. And on the x-axis, you have the eccentricity. So here, circular, very elliptical. And so what we see is that if we have a no kick, then we expect actually almost all of our systems to just be circular. However, if we simulate a very strong neutron star kick, just like the ones we see with neutron stars, and you can see it better on this right plot, you can see that all of our eccentricities are expected to be much higher. And so by looking at the eccentricity, we basically can tell something about the kick that black holes receive, which is one of the main questions in black hole formation. And something similar can be done with the orbital periods. This is a little bit of a more complicated plot, but so the period is on the y-axis, and you have to see it as a distribution that is just tilted. So instead of the histogram I showed you earlier like this, just look at it like this. So the wider this is, the more systems we expect to find there. And the main difference here between the no kick on the left and the strong neutron star kick on the right is that we see that if we have a strong kick, we're lacking binaries at long periods. And this actually makes a lot of sense, because the longer periods are less gravitationally bound, and hence a kick will more easily disrupt the binary. So we're just not seeing the binaries there, or much less there. So I hope this convinced you that we can learn something about black hole formation. However, there is one thing, and I kind of mentioned it in the slide, like we have a lot of these systems that initially looked like black holes, but now they don't anymore. So we want to see how are we affected with Gaia in this regard. And so for this, we looked at a couple of systems that have no black holes. So first, we have just two stars next to each other in a binary. We also looked at triples. And then we looked at blue supergiant primaries, which means that the most massive star is already evolved, is quite big, very luminous. And so what we find is that actually with our AMRF method, we shouldn't really worry about this. So this is really amazing. And hence we can conclude that just with the sample of Gaia, we can find about 100 of these OB plus black hole binaries and learn about black hole formation. However, as it turns out, in order to see whether this works or not, we will have to wait a little bit for the next Gaia data release, which might be somewhere at the beginning of 2026 or the end of 2025. In the meantime, of course, we don't sit still and we just continue doing some science, and this brings us to BE stars, to the next question in the evolution. So the other question I mentioned was, how do the interactions happen? How do they work? And in order to do this, we need these BE binaries. What is a BE star? By definition, it's a rapidly rotating B star with a decretion disk. And the B star just means massive star, at least in this case. Then let's look at the other aspects. So here you see a part of the spectrum, so a part of this rainbow. You can see here the wavelength, and here what we call normalized flux. So if we just have a continuous light source, then you expect it at 1. However, absorption lines, light is blocked, so you see a dip. You see less flux. And if you look at a normal OB star model, we expect these nice absorption lines that you can see here, for example, for hydrogen, H-alpha. If we look at the decretion disk of a BE star, it's not a nice absorption line. Instead, it's even emission, which means we have an excess of photons there. And one thing that is with these emission lines is, as you can see here, this is a couple of spectra. You observe them at a different time, and these lines look completely different. And of course, if we now want to see what is the motion of these stars, I hope you agree that it becomes quite difficult to see what is the true motion of these stars and what is variability in the disk. So this makes it quite challenging. Then we move on to the rapid rotation. So if we have again our standard model, which is fairly narrowly, slowly rotating, you can see a very narrow absorption line. This is another element, this is helium, again part of the spectrum. If we look at our BE star, very rapidly rotating, very stretched out, and as I told you, in the spectrum we also see this very stretched out. This is actually still quite a nice example, but this becomes very challenging to find these spectral lines. They can easily be hidden in the spectrum. And so these two aspects, these emission lines and this rapid rotation, make BE stars very challenging to analyze. However, they are probably quite important for the evolution. Because recent studies, a lot of recent studies, suggested that the majority of these BE stars are formed through binary interaction. How would that be? Well, as I said, we at some point have mass transfer. We're dumping some mass. We're transferring mass on this other star. You have the spin-up of this star, which creates our BE star. But so you need this mass transfer, this angular momentum transfer, to spin it up. And hence, these binaries are very important to study binary interactions, because if we fully characterize these systems, we can start modeling them and we can start tracing back how they actually formed. And so, of course, it's important to know what the companion is. And this brings us to one of the BE binaries called MWC656, which was the only reported BE plus black hole binary. So MWC656 was said to have a black hole between 4 and 7 solar mass. And this was, sorry, this went a bit wrong here, but this was reported from this line, the iron 2 line. As you can see, it's in emission, a flux higher than 1, so this comes from the disk. But so what we did is we actually tried to, or we obtained some more spectra, and then we're going to look at the motion of the star, which we can see here. So this is a helium-2 line. This is a different line, also in emission, so it comes from a disk. And what you see here is we just stacked all the spectra on top of each other, and we can see this very nice, clear motion of the star, almost sinusoidal. Now, if I do the same thing, looking at the motion of another line, for example, H beta, a hydrogen line, also in emission, but I hope you agree with me that I don't see the same motion as I saw for this helium-2 line. And this basically tells us that there are two components in this system, the one belonging to the helium-2 line and the one belonging to these hydrogen lines. And so what we can do is we're going to calculate the radial velocities, which basically tells us the motion of the star, and we can find an orbital solution for this. So what you see here is the orbital solution. So you have our radial velocities on the x-axis, and you have the phase in the orbit, so at which time in the orbit am I, on the x-axis. And as you can see here the radial velocities. And if we fit this, we find all the parameters. We find the period, we find the eccentricity, and we find two very important parameters as well, which are the radial velocity semi-amplitudes. What are these? They are indicated here. This basically is how far does it move away from the center of mass? How rapidly does it move? And these are these two values, which we call k. And if we have these two k's, we can actually obtain the mass ratio. Okay, and this mass ratio alone might not tell you much, but if we combine this with an estimate for the mass of the BE star, we can actually find the mass of the companion. And in this case, it's between 0.6 and 2.4 solar mass. Now, if I look back at the endings of stars, our white dwarf, neutron star, and black hole, I can see that with a mass of 2.4, it's very unlikely that it's a black hole of 4 to 7 solar mass. So what we concluded for MWC 656 is a new mass ratio, but more importantly, it's unlikely to have a black hole. Moreover, what we did is we not only used this hydrogen line, we used several other lines in the spectrum, calculated radial velocities and orbital solutions. And what we find is that whatever line we used, basically our results are robust, which is a very important result for BE stars. As I told you, they are very challenging. But that is not all we did with BE stars. We did something with BE X-ray binaries. Why BE X-ray binaries? Because the BE stars are said to be here, the X-ray binaries are all the way down there. Well, as it turns out, we don't really currently have a population of BE binaries. As I said, they're very challenging, so it's very hard to find them. And what we want to do is we want to use BE X-ray binaries to actually calibrate a good methodology to potentially find our BE population and then trace back our mass transfer. So BE X-ray binaries, what does this mean? Or why do we want to use them? Well, we can have a lot of information from these X-rays. First off, we might be able to find the orbital period, because as the compact object moves through the disk of the BE star, we have some X-ray bright flares, outbursts, and this might then tell us the period. On top of that, there is something called an X-ray pulsar. And if we see one, we know we have a neutron star companion. What is an X-ray pulsar? It's kind of in the animation here. What happens is that a lot of energy is channeled out from the magnetic field lines, from the poles of this neutron star, and this neutron star is very rapidly spinning. And if it's a little bit tilted, just like in the animation, sometimes, right now, you will see an X-ray flare coming up. And these X-ray flares, these pulsars, exactly can only happen for these neutron stars. So the period and this neutron star information can actually help us to calibrate our spectroscopy. We can see if we use different lines, do we get the same results? Do we get a mass for a neutron star? Do we get a decent period? And so this might help us say, like, for example, this iron 2 line that we had earlier, good line. You can use this one. On the other hand, the H-alpha line, that you see here, this often variable line, you should be a bit cautious when you use this line. And so by doing this, by calibrating the methods and spectral lines, we really want to develop a methodology to study these BE binaries. So in conclusion, what are the main conclusions of this thesis? First off, we had trying to find these single degenerate massive binaries. What we found is that Gaia will be able to detect over 100 of these single degenerate binaries. And from this, we would not only increase our sample tremendously, but we would actually learn something about the black hole formation scenario, which is great. Secondly, we looked at these BE binaries, and we tried to answer, or we looked at the question of how do the interactions form. And while we are not solving this question right now, we showed that there are 0 BE plus black hole binaries existing, which is an important result as well. Why are they not there? And then the BE analysis of these X-ray binaries could really help us to actually calibrate and improve our methodology to finally find this BE population and then really study how these binary interactions work. Thank you very much.
Thank you, Soetkin, for a very clear presentation. So now it's time for questions from the examination team. And I suggest to start with Professor Lena, who's the external member from Amsterdam. And then we can go to the questions from Sylvia for the past 2 weeks. So go ahead. If you would like to, no, you can sit. You would like to have a microphone?
You could have following online.
Yes. Okay. Then is it working?
But is it on? I want to borrow this.
Yeah, maybe you just stand here.
All right. Let me start by congratulating you on completing this beautiful thesis. It's really an impressive work, and I greatly enjoyed reading it, and I actually also learned a lot from it. So for that reason, I feel very fortunate to having this opportunity to pick your brain a bit about your thesis. And I'll just go from front to back with a couple of questions that I would like to ask you about. So I'm going to start with actually with the introduction. Like on page 8, you mentioned this very interesting black hole candidate in NGC 1850. And it was actually for the very first time that I read about it. Somehow this object was not on my radar. So you mentioned actually that an in-depth analysis was performed, but that some more additional data analysis needed in order to settle on the nature of the companion. So I was just wondering if you know what kind of data analysis would be needed to find out if this is a black hole or not.
Interesting question. So this is, to get the audience along, this was also one of the candidates that was a black hole, but turned out to probably not be a black hole anymore. And so the reason they asked for additional data is because one of these research teams, they analyzed, I believe, some infrared data that was then part of that could tell you something about the disk, whether it was like just an optically, or a dust-blocked star, like not very visible in the optical. But they concluded that you can't really say anything from these data either. I don't know, I think probably that, I can't remember the resolution or like how many epochs they had or something, but one thing that we always like to do is collect even more spectroscopic data, because I can't remember if they did spectral disentangling or not. But spectral disentangling is a technique where you're going to try to separate the two spectra of the stars. So you're going to find the first star and the second star in separate spectra. But you need a lot of good, high-resolution, high signal-to-noise data. So my first idea would to also do that just like we did for all the other ones.
Yeah.
Yeah.
All right, I get it. As an observer myself, I blindly agree. We always need more data, for sure. Right. I also had a question on your figure 1.2 on page 10, where which shows a comparison between the compactness and carbon-oxygen mass of the core.
Mm-hmm.
And you can actually see some differences between the single star graphs and the binary ones.
Mm-hmm.
And it wasn't completely intuitively to me actually why that would be the case. So I was wondering if you could explain me why we see those differences.
So, as I understand it, when you have these binary interactions, well, so depending on which star you're looking at, I think they are looking at the primary star, or well, the second, anyway. So either you expel the envelope, right? So you're gonna be left with this kind of either fully helium core, or just a little bit left of the envelope. And I think this will kind of change the internal structure of the star, because you have a lot of less mass at the moment, so it might kind of try to balance it out. On the other hand, if you have the mass gainer, you will get a lot of more mass in the envelope, which probably also will just change a little bit of the core structure, might increase it or something. And I think that's the basic difference that we have from there, just because of these changes in mass that will alter the internal structure of the star as well.
Yeah, that sounds interesting. Yeah, sounds good. Might be. All right. Then I also had a question on chapter 4, which is actually related to the demographics of BE stars, which is also important for your chapter 5. But in your chapter 4, you mentioned that about 70% of the BE stars are predicted to have a white dwarf companion. And unfortunately, none are found in the Milky Way, although we know a couple in the Magellanic Cloud. So I was just wondering, what are your thoughts of why don't we find them in the Milky Way? And where are they?
So white dwarfs are, of course, much less massive than our neutron stars and black holes. So if we look at spectroscopy, if we're going to try to look for these radial velocity variations in these already challenging objects, it becomes quite difficult to find such a low mass companion, at least in spectroscopy already, because the more massive your object is orbiting around the least massive object, the less this star will move. So then in the spectrum also, these spectral lines will move much less already in the chaotic, noisy data. So I think that's one of the main reasons. Of course, also with the high energy data, I don't know exactly how bright they would be in X-rays. I think also much less bright. So then our X-rays could also not necessarily fully help us there, I think.
Yeah, I guess that might be right. We're probably biased towards like the neutron stars and any black holes that might be there in the X-rays, yeah, and the radio as well. Yeah. All right. So, as I was very impressed by your work, I also look very much forward to seeing what next, what you're going to do next. So, in your chapter 6, where you provide basically an outlook of this research field, you mention like things that are coming up. Of course, data of Gaia data release 4 is going to be very important, and you measure UVX as well as a new mission that's coming online in 2030s. But I was just wondering, like, are there any other plans on the horizon, like other types of surveys or specific source samples that we might be targeting, or maybe other wavelengths, but specifically some kind of surveys perhaps that would be worthwhile?
So I think there are a lot of upcoming missions that are now photometric missions, I think, that are just constantly taking images of the sky, of all the stars. And so while this would not necessarily be in the binary or single degenerate binary aspect, I think they will help a lot with finding all of these supernovae, all these transient objects that we might find. If we could instantly do some follow-up data of those if we find them. So for example, I think the Vera Rubin, am I wrong? Vera Rubin Observatory will also be one of these missions. We have the BlackJam, and Meerkat missions, which are currently already ongoing, right? And so I think there is also actually quite a bright future in these kind of missions as well,
Mhm.
hopefully.
Yeah. All right. Let's hope so. Yeah.
Yeah.
All right. If I may, I have one final question.
You may.
Is that okay? So, in several parts of the thesis, I guess, and most prominently in chapter 2, you mention that there is this discrepancy between what you expect theoretically for how many of these OB and black hole systems there must be and how many we've actually found. And you make a point that actually there's issues both on the theory side and on the observational side, likely, right? That cause this discrepancy. So I was just wondering, which of the two areas do you think we're going to improve soonest?
Soonest, okay. Well, I think it's hard to improve in theory if you don't have observations to calibrate. So in that sense, I certainly hope that we must find, or we must look for these black holes. So I think observations will most likely improve, maybe in 2 years. Okay.
We didn't know.
But yeah, so I think once we have these observations, like even if we don't find anything, we might be able to, well, first look into like, is it normal that we don't find anything? And then really start thinking into theory, okay, we know this is definitely something we need to work on and start to trace why this is the case.
Sounds good. Yeah, thank you very much.
Then I suggest that the UC or the supervisors will read the questions from Professor Tonnen.
Professor Thorne couldn't be with us today, but she's online. She's been watching the presentation, and she sent me 2 questions that contains a number of sub-questions. The first one is on MWC 656.
Okay.
Well, you know that the nature of the companion remain uncertain. In the case that the companion is O-type subdwarf, so an SDO, or if it is a white dwarf, what would you think would be the endpoint of the evolution of the system?
So these hot subdwarf were these helium stars that I mentioned, these very hot objects. What would be the endpoint? I think given the amount of mass so if the BE star will grow, right, this is a massive star, so it will rapidly grow during its evolution. So I think maybe a common envelope might be a scenario that could happen, especially for the white dwarf, because it's not really accreting a lot. I don't know about how much hot subdwarfs would accrete theoretically. So that if we would have this common envelope, most likely we will have a drastic shrinkage of the orbit. Either we get the envelope expelled or we have a merger if we really keep on shrinking. But common envelope is really something we absolutely don't understand.
And then there's 2 further sub-questions. Could it lead to a supernova? And would it be a gravitational wave source?
So you mean the white dwarf or hot sub? Yeah, well, I guess.
With the companion.
Yeah. So what happens with the white dwarf, it has a certain upper limit that it can be a white dwarf, and this is 1.4 solar mass. If the white dwarf would exceed this mass, we typically may say it goes type 1a supernova. So I think this is what Sylvia means with this question. So as it turns out, of course, the white dwarf would have to accrete mass for this. It would have to gain mass. And as it turns out, according to a lot of theory simulations, white dwarfs don't really accrete, at least not from the BE star. It wouldn't accrete that much because there's too much mass rapidly transferred. So the type 1a supernova is probably unlikely. And the hot subdwarf probably might go supernova. We don't know, right? Gravitational wave source. So I talked about the current gravitational wave sources, which were compact object mergers. However, in future generations, we will go much lower, or extreme mass ratio, go to white dwarfs as well. And then it will just depend on what the final orbit is that will get out, that it might potentially indeed also become a gravitational wave merger.
All right. There's another question. This other question is on, you put a lot of emphasis in the introduction on the description of binary interactions. And one of the motivation is to use this information to improve on the predictions of gravitational waves, right? So what do you think are the most uncertain steps, and where and how do you think that electromagnetic observations, so not gravitational wave, can help actually to make significant improvement in the coming years?
So the most uncertain steps in this example of binary evolution that I showed, I guess she means.
And then the evolution and the formation of gravitational wave
Yeah.
sources. So in this entire diagram that you
Yeah.
show.
So first off, we don't really know for sure that these double massive binaries could fully evolve, at least not the current ones, could still evolve towards gravitational waves. There are more options. You could have, for example, two black holes that you dynamically catch, and then they might merge. I'm sorry, I'm trying to think back at the question.
Uncertainties?
Uncertainties.
And how you fix them?
And how I fix them, yes. So the thing is, I think it's really crucial that we really try to find as many of these intermediate steps as possible. Then, of course, that will depend on how our knowledge of theory is currently progressing, but we can see if we find a BE binary, how it went, first of all, to trace back to this mass transfer, and then also, can it evolve forward? How will it evolve forward? Could it potentially, according to our current theories, be a gravitational wave progenitor? And the major uncertainties, well, I think, I'm a bit biased, of course, right? But one of the major uncertainties I really think is currently this black hole formation. Because if we just kick them out of the system, we can't form, well, we disrupt the binaries, so we don't have any binaries left. Of course, as I said, common envelope is uncertain because we don't really understand. We don't even know whether it has to happen. There are recent studies that suggest maybe we can do it a little bit less unstable, less, I would suggest more conservative, for example, just nicely transfer the mass. This whole mass transfer thing as well, like we know it we know it must happen, but it's kind of the question of how much mass get transferred onto the other star. And I think it's a really difficult question to answer.
How do you think electromagnetic observations
Right,
can help?
yes.
That's the last part of the question.
So, yeah, I think, so the thing is spectroscopy tells us a lot of information on both the systems. Like I said, if we can find these BE binaries, we have a BE star plus hot subdwarfs, we find the masses of both stars, we can fully trace the system back, but also forward. But of course, it's quite tedious because you need a lot of spectra, high resolution, and everything. I think astrometry as well is quite useful because you can instantly see all the binaries and you get a lot of information from there as well. Yeah, maybe we should do more with the X-rays as well, but then target those binaries more in spectroscopy or other kinds of data, like photometry, kind of trace the light, how it changes of these sources. And I think what we need is really like this multi-messenger in all kinds of wavelengths to really understand what is happening.
Okay, thank you.
Thank you, Luc, or I should say thank you, Sylvia. Then maybe it's time now for the local professors in Leuven, and we can start with Jon.
I can stand here. That's all right. Okay. Thanks, Soetkin, for a very nice thesis, as I've said before, and also for an outstanding presentation today. Very well done. I thought I'd take this opportunity to chat a little bit with you about BE binaries. And one thing that I'm a little bit curious about in this system, and you actually showed a very nice figure of it today, is your helium-2 line. Yeah, this one. This yeah?
One, yes.
Yes. And, you know, I completely agree with the key interpretation that you have two components here, two companions here, right? But I do wonder, why would this line be in emission?
So the fact that it's in emission tells us that, well, or in this case, it probably tells us it comes from another disk from around the companion. So here it would probably belong to this accretion disk around, well, the unknown object that is unlikely the black hole. But so the fact that it's a helium-2 line we need a lot of energy to actually see this line, so it must be quite a hot disk, quite hot objects. And the BE star can't do that. It's too cool to excite this helium-2.
Yeah. So doesn't this bring us strong clues to what the companion must be then? Because not all, you can't just say that it's an accretion disk, it has helium-2.
Yes.
So what would you think it is then, based on this only?
I really don't think, or well, at least to my knowledge, I don't know if we can really say something about this, because we also see helium-1 lines, for example, in emission in BE star disks. So that means there is also quite some helium in these. So if you just transfer the mass on that, you could just have the hot object of the white dwarf, subdwarf, or neutron star heating up the disk, I think.
And is this a common? Do the other candidates also show this type of emission?
So there are some other BE plus stripped stars plus hot helium stars that do show this helium-2 emission as well.
Yeah.
According to my knowledge, much less strong, but it is there. There is some knowledge in some white dwarf binaries, I think mostly cataclysmic variables, so just, the accreting white dwarfs, that also show this.
Mm-hmm.
Not really sure about neutron stars, but...
Seems unlikely to me.
Okay, yeah,
but
maybe.
I don't know, that's why I'm asking. I thought that this was a thing that one, it sticks out very much.
Yeah, maybe you're absolutely right,
Yeah.
but I couldn't say for sure.
Right.
I don't know.
Right.
I think we should try to really model the disk like with different objects, and maybe now in the institute we could start doing that with the new
Perhaps.
postdoc.
So that actually brings me then to so to say my next, because if you have these type of, okay, you also for the other candidates you mentioned this LB1 and there are others, there are these type of peculiar features indicating some sort of accretion disk around the secondary here, right? Now, but wouldn't that mean that all of these BE binaries would essentially be what we call BE X-ray binaries, if they have this type of accretion disk, if that's the only interpretation that works?
So,
which they're not, I assume.
I don't think they're X-ray bright. No, you're right.
I don't know, but yeah.
So one thing, of course, because of this disk already, the BE star itself, so there has been a study that studied BE stars in both X-rays and in radio, I think, as well.
Yeah.
So what they find is, at least in their sample, they're already all somehow showing some X-rays and some radio. Of course, not as bright as these real X-ray binaries. Yeah. But also this one, actually, if we look at how bright it is in X-rays, it's not that much standing out compared to the other ones. So in the disk itself of this BE star, you already have a lot of these things going on, so this also shines some X-rays. So I don't necessarily think, I think the accretion on the compact objects will be a much brighter X-rays, of course, than when you would have for example, a hot subdwarf accreting.
Right. It could be. But so that brings me then to so to say the last, because there is a big population here or of BE stars, of course, like I think you mentioned in your thesis, something like 20% of all BE stars, right, which is huge. And the formation scenario now that you advocate for is the binary channel, right? But it seems to me you indicated that you had like 70% that were accretion, well, they were white dwarfs, right? So to me, it's not really clear why would these have so different signals than those type of systems? Why don't more or less all of the BE stars have this type of behavior?
I think it's also, so this system is also quite short period.
Right.
It's in the order of a month. So it really gives the companion the opportunity or the possibility to go through the disk and gain some mass for an accretion disk. I think if you have much larger orbits, of course, your mass doesn't get there, at least not yet. maybe if the B star evolves and stuff. But so maybe, yeah, they're all not in the right period range to actually get the accretion going, and hence we don't see them.
Yeah.
I think, yeah, it's mostly the short period orbits
period,
we might be able to
Right.
see these kind of things.
I see.
But, yeah.
Okay, yeah. That was all from my side this time. Okay, and congratulations, Jan.
Thank you.
Yes.
Thank you, Jan. Maybe, Joris, you have questions for Soetkin? Please.
Thank you, Soetkin, for this very nice talk. I really enjoyed it. So I actually have 2 questions. As you may know, the Gaia spacecraft will stop operating in January of next year. We still have a backlog of observations, but they're already thinking about a successor, as you may not know, Gaia Near, Gaia in the near infrared. And so the last time I asked you, can this help you? You answered infrared. We don't need no sleeping infrared. I am interested in hot blue stars. But there are also other advantages to a second Gaia. One is you double basically the number of observations per source. If you combine it with Gaia, you cover a period of more than 20 or even 30 years. Does this not help you at all in your quest for black holes?
Of course, it won't help at all. There is always, like I said, additional data is always great. I think the only thing is that with our massive stars, they are very hot, so they shine very near the blue wavelengths and the ultraviolet. So the infrared wavelengths are a bit dimmer. Of course, we will still see them there. But I think one of the nice advantages there as well is that the BE stars might be or bright there as well. And so we could learn a lot from maybe these binaries more over in these wavelengths as well than just in the Gaia itself.
Also to eliminate false positives, or not?
I'm not really sure if even a very low mass star would shine bright, would outshine, so to say, the massive star even in those wavelengths. But for sure, like if you increase your data from 10 years to 20 years, you can even also go up to much larger orbits, of course. So I think you really extend your whole parameter space that you can explore. And of course, yeah, if you trace the orbit even more times, you'll reduce error bars. And I just don't know if it would have the same error precision, of course. But then, yeah.
My second question, so you mentioned we want to find all the black holes. I didn't see lensing, and I was wondering, is that completely negligible? Do you expect most of the most of the black holes to find in binaries with the method you showed, or is there a significant fraction you also need to find with lenses?
So we asked about lenses, and I have a little... there it is. I have a little slide about lensing. So it's true, there are more methods than I showed you to search for compact objects. And one of them is what we call microlensing. So what happens is that when you have just a black hole free floating in the galaxy, it might at some point pass another star. And what will happen is, and this you can see in the animation as well, is because the black hole has such a large gravity, some of the light rays that are just normally not reaching us will be bent towards us. And so what will happen is the star, all of a sudden, we have more light, and so the star will flare up in the optical. It will become much more brighter. If we analyze this data, we can kind of find out what this object was that lensed the star. And I think it's already one of the oldest techniques that we are kind of using. And I think people still expect to find a lot of these. I think for neutron stars, we have quite some, and for white dwarfs as well, I think we have quite some examples. However, there is only one black hole currently that is found by this. I don't know why. Well, this is, I guess, another question. Why are we not finding these then? I wouldn't be able to say whether it's like just our data quality or just because we're not. So I think these missions like Black Gem and stuff, maybe they will also help us find way more of these kind of microlensing events. But of course, if we find this black hole, it becomes quite difficult to say how it evolved in the binary, of course. But from these microlensing events, they can also actually trace back whether it got a kick or not, which I think is, which they try to do with the one black hole, but they can't say it because it's only one, and some uncertainties. But
and about the black holes not in binaries,
so I think their microlensing might be one of the only options we have, because otherwise we can't really see a black object floating around in space. So for those, I really think we should monitor the sky. Well, we're already monitoring it so much, but yeah.
Okay, thank you. From my side.
Maybe Pablo, if you would like to ask some questions.
Should I just grab this so people can hear me better? So, well, thanks a lot. That was a great presentation. I'm in a bit of this gray area where maybe I should say I've already asked you enough, but I'm not formally one of your supervisors, so I will ask something. So, my question is a bit of an annoying hypothetical.
Okay.
So, we already suffered a bit through Gaia DR3. We didn't get what we wanted, and we're hoping for DR4. So the question is, what if DR4 is also stingy with the binary solutions, but gives you the epoch astrometry? Would you be in a position to use that information, or would it be overwhelming to you?
Well, I believe at first it will be, I think, overwhelming. You have a lot of data points from a lot of stars. So if they don't give me, so I'll phrase it otherwise. If they don't give me the binary solutions instantly, I will first have to fit all of these binary solutions myself, which means I will have this catalog of 20,000 massive stars that I would have to fit myself. Well, science is teamwork, right? But basically, you do the work yourself. As a team, you can also do it yourself, right? I'm sorry. You know what I mean. And I do think, yeah, it's one of the things I'm already in the back of my mind. It's something we should really take into account, that there will be some time for me to prepare getting all the data, fitting all the data, and then only trying with the AMRF, trying to find them. And probably at first that will be a bit overwhelming, yeah.
Yeah, and I guess the follow-up is like in the sense of how this would go in the end. You would like to follow up these objects and then potentially do full fitting with spectroscopic and astrometric observations.
Yes.
So in that case, wouldn't you already need to have the machinery to do the astrometric fits as well? So is that something you would aim to do a combined fit of the spectroscopy and the astrometry to get better solutions?
Yes, that. Actually, I didn't yet think about this, but now that you mention it, definitely yes. I think it's always, but I mean, it's amazing that you just get these orbit binary solutions anyhow from the Gaia DPAC team. They're doing a lot of great work. Of course, it's always very nice to double check that if you get the additional information, that it still makes sense, because sometimes if you fit from the one kind of data, maybe you have a very large distribution or something, or in one of the parameters, and then with spectroscopy you could really start combining it and narrow it down a little bit. So I think that would be very useful to fit both of them together. Of course, I must say maybe it's better to first just use astrometry to find the candidates and only then do the combined fit, because otherwise doing that on 20,000 stars is a bit a lot.
Okay, well, that's it from me. Thanks.
Do the supervisors, Omar or Uk, still have questions? You're good?
I was not planning to ask any question, but it's way too soon for lunch, so we can spend a little more time. So you've been working on the topic, or two different related questions for about 4 years, and it turns out that usually it's much easier when you know the solution than when you don't know the solution. So after 4 years, you and us together, right, as a team, you have made a lot of progress. And I would like now for you to look a little bit back over the last 4 years and knowing what all you've learned. If we would have to tackle the same problem, is there anything that you would have changed or you would have done differently? Except changing supervisor.
Oh, no, no.
You can say that after the proclamation.
So at least in the first part, we spent a whole lot of time on. So actually, when we proposed this PhD, we first had a little other project in the beginning, which was also using a little bit of interferometry or astrometric data. But then when we started PhD, we were like, you know, actually 1.5 years or something, it's not really that long. So it's better to first prepare for Gaia, and then if you have spare time, you can do something else. In hindsight, we could have just done the first thing. But I don't know if I would really change the order, because I think it was actually, I really liked doing it. You were like, oh, I'm working towards a deadline, okay, and then the deadline came, and okay, it wasn't really that exciting. But I think it was still, I really liked still doing the Gaia first, I think. It's, otherwise, okay, now that we know, but otherwise it would have been so stressful. And it was already quite stressful to get the deadline. Maybe, I'm very sorry, Sylvia, but I also spent a lot of time on the triple simulations, and as it really turns out, these triples were not really a cause of problems for our simulations. So maybe I could have just done a little bit less on these, at least, instead of trying to figure out all the plots that I had on these triples, or the configurations and all kinds of stuff. Yeah.
All right, thank you. We'll talk more later.
Anyone else questions?
I have one more question.
Yes.
And I first want to say, you not only have shown a talent for research, but also for presentations. It was very impressive. You mentioned that the thing you do not understand, or humanity doesn't understand, is black hole formation to a sufficient level.
Mm-hmm.
And to me, it's not fully clear, what do we not understand? Is it the laws of physics that should explain us how black holes form? Or is it more that the system is this complex? Like prediction of the weather, we know every bit of fundamental physics that goes into the weather, yet we have a hard time predicting the weather. Which of the two would it be?
I don't think we have the full physics in our knowledge to what happens in the black hole formation. I mean, to be honest, we don't even know what the black hole is in itself. Like mathematically, we can explain it, right? But we don't really know. So I think definitely, I mean, there probably is something missing. It would be amazing if we knew it all, but I don't think that is, in this case, a possibility. And what was the first option again?
Whether it's a lack of knowledge of the laws of physics, or it's for the complexity of the system?
The complexity of the system. I think, I mean, there happens, it's such a short time scale, so many things happen on this short time scale, so much energy, neutrinos fly away, mass is lost and everything, and I think it's such a complex system that that it's very hard to model as well. Like, you get different solutions when you model, like when you change a teeny tiny parameter, probably might get something different. And so it probably just might be a combination of both, actually.
Thank you. Since it's a public defense, the public might want to disagree with the results, or challenge the results, or simply have a question about the results. En je kan die vraag ook in het Nederlands stellen als je dat wilt. So if anybody has a question.
I won't do it in Dutch, but that's okay, I can speak that. MWC 656, you disproved you killed the black hole off by arguing that it's
Yeah.
LBK has started finding black holes that fill the mass gap. The 2.4 isn't really that out of range. Does that bring the black hole back into consideration?
So Reynolds' question is about basically the upper mass of the companion of MWC 656, which was 2.4 solar mass. And on my slides, I mentioned black holes more than 5 solar mass. And this basically originates in what we find observationally, more or less, a mass gap. So this means that we don't find any objects between the most massive neutron stars and, let's say, about 5 solar mass black holes. And we have this kind of gray area in between where we don't know whether objects should be there. Well, theoretically we think so, but we don't find them. So it might be observational as well. 2.4, of course, okay, so first of all, this 2.4 is within 1 sigma. If you go a little bit further, you might still increase it to 3 or something. So then you could have indeed a lower mass gap black hole. I think with the 2.4, it's anyway quite uncertain because we have these kind of high mass neutron stars. We can't really distinguish between neutron star and black hole just from this optical spectroscopy. And the X-rays are not sufficient either to do that. So I guess I'll rephrase that it's very unlikely to have a 4 to 7 solar mass black hole, at least. For that, I think we can agree on. What the nature is of this 2.4 solar mass object, I would say it's maybe more likely to be a neutron star, but I can't 100% exclude, of course. Yeah.
Are you satisfied with the answer?
Yes.
Any more questions? If no more questions, then there's one more question.
Can you go to slide 9?
Very specific.
I'll get there. Oh. This one? Yeah?
So at the third stage, we have the helium star plus BE star.
Yes?
And the fifth stage, we have OB plus BH.
Yes.
So is it expected that the BE phenomenon kind of dies out somewhere in between? Or what percent of these OB companions are expected to be fast rotators?
Very interesting question, especially on the... what Kunal asked was, so in this part you see helium star plus BE, whether here you just see OB star. And so the question is, do we expect the BE phenomenon to disappear, or how many rapid rotators, BE stars, do we expect here? I can really not give you a number on the amount. As was mentioned, about 20% of the B stars look like or are BE stars. So maybe something along, but I mean, I can't put a number on that one. The thing with BE stars is that the phenomenon itself, how this disk, so BE stars are really characterized by the disk. The disk is what makes us classify them as BE stars. We see rapidly rotating stars without the disks, so they're not BE stars. And I guess that's something else we don't know about BE stars is how does this disk form, like why is the disk there? Sometimes it can even disappear on timescales of years and then reappear, and we don't really know why. One of the major uncertainties. So I mean, I guess you can, well, that's the question, right? Do BE plus black holes exist? Because we didn't find them either. And according to theory, it's quite difficult to form them because of the mass ratios and something, the mass transfer should be not ideal to form a BE star. So it becomes quite difficult, I think, to find them here, but I can't say for sure unless we find all the BE binaries and say that there are no black holes, of course.
Yep. People are getting hungry, I assume, but you can still ask questions if you want. Okay, if not, then the examination committee will now gather and we will be back soon. Ladies and gentlemen, dear colleagues, I will now proclaim the result of the deliberation by the examination committee appointed for granting the doctoral degree in science in astronomy and astrophysics. Soetkin Janssens has presented to the faculty the PhD thesis on the topic of the search for massive single degenerate binaries in the Milky Way in partial fulfillment of requirements for the PhD in science in astronomy and astrophysics. And Soetkin Janssens has defended this thesis in a public session before the examination committee. The examination committee has determined that all requirements concerning the granting of the doctoral degree that are prescribed by the law and by the university regulations have been met. Therefore, on behalf of the rector of KU Leuven, I confer upon Soetkin Janssens the degree of Doctor in Science in Astronomy and Astrophysics. Now comes an important part. By obtaining the doctoral degree, you commit yourself as a doctor to act also in the future in accordance with the basic principles of research integrity as described in the ALEA European Code of Conduct: reliability, honesty, respect, and accountability. I close the session.
Because then it's done, and then we don't forget about it.
You have to sign, because otherwise it's not valid. Here.
In front of you. Yeah, you okay? You can sit down, yes. It's gonna be very long. Dear Soetkin, dear Dr. Soetkin, dear Dr. Janssens, it's always a pleasure to be the first to congratulate the new doctor, and certainly congratulations to you for the beautiful work that you've done over the last 4 years. And before I forget, immediately to thank you for your participation in the group and the life of the Institute. That has been really a pleasure to have you. And to the family, thank you for allowing me to borrow Soetkin for so many hours. So Soetkin has been telling me about her view of what happened in the last 4 years, and I'm going to tell my view about what happens in the last 4 years. So when you think about Soetkin, or when I think about Soetkin, there's a few keywords that come to my mind. In astrophysics, we like to use keywords, right? When you make a publication, you need to specify keywords. You write 10 pages, but at the end, it's all about 10 keywords. It's intelligence, humor, swimming, cookie, energy, for example, and I have a little story about all of those words. And intelligence you've seen, right? But I'm impressed when I look back at 4 years and also 5 years, because you did your thesis, your master thesis with Tomer here, is the number of different techniques that you've been using and you've been able to combine to make a very good progress on a topic that was also for us difficult, because we have never done astrometry before, right? So we came with an idea, we had a goal, which is to say, can we find this black hole with Gaia, and if so, what do we learn? But we didn't know anything about it, right? So this is maybe one of the boldest theses that we started, obviously that I started. Quite often I had a better plan, but we created the plan as a team, and then you executed it as a team. That's true. For the humor, I'm not going to talk about that because that's not for the broad audience. But I remember many good love that we had. You were also passing in front of my office every morning, so most of the morning. So this is great. Something that Soetkin has, of course, is a lot of energy. She invests that in swimming, but she invests that in everything that she is doing. But she's also the ability to feel opportunities. Because, for example, when we stopped having cookies at the Institute, she immediately set up a business. She's been selling hundreds of boxes of cookies. This is true, huh? And the goal was that she could keep doing sport at a high level and keep being fit, while everybody else in the Institute was actually getting fatter and fatter. And me, I've done my measurements. I can show you the curve. And actually, there's something related to that. Of course, it's because you wanted to continue doing sport at a high level, swimming at a high level, and you managed to combine those perfectly and never had any feeling that the fact that you were spending time and energy in swimming was actually hurting your PhD. So you balance that perfectly. I think even there, the fact that you were doing high energy thing was also allowing you to stuff that were on your mind, you could put them on the side. And what I wanted to do the comparison, because it's coming from Alex de Coter, but actually I saw that you've done it in your thesis, is to compare what we do in astrophysics or in science as in academia as a top-level sport. That comparison is not coming from you, it's coming from Alex de Coter. He's also very much into sport. So Alex de Coter is a professor both at Amsterdam and here in Leuven, and he was my mentor when I was a postdoc in Amsterdam. So he was comparing that, and he was mentioning, for example, that you spend a lot of time in the training, that the preparation takes a lot of time, that the moment of performance do not just focus, but that you can get a lot of pleasure and a lot of proudness about those moments. It's actually the words that you've been using in your thesis. So for those that have not read it, I think it's the first page of the thesis. It's worth reading. It's a nice comparison. Of course, same with sports, there are difficult moments. So part of those difficulties, for example, the ability to tackle something completely new, so the learning curve was there, as I mentioned. The frustration that Gaia did not release those data that we needed. The challenge of the BE binaries, because those BE binaries is somebody that everybody, I mean, every people that have been working on it have realized it's a very complex system because of all the physics and the time scale of the variability and things that we don't understand. The stress of what the future has in store for you, the up and down of the geopolitics that has impacted you. So thesis is not done in a vacuum, but it is done in a context. And as you explained in your comparison, you just have to push through this, or at least that's the way you have presented it. So I think one of the key feature or trait of character that has allowed you to push through this is really the motivation. And it's the same as sports, the internal motivation of the sport person, the sportman or sportwoman, is something fundamental in her performances. And I think for PhD or for scientists in general, you can do science for many, many reasons, but if you don't have the very personal motivations to do that because you like it, it's harder. So this professional motivation is a strong asset that you clearly have. And at the end of your paragraph, you say, I'm going to keep swimming. I hope you're going to keep doing science too. There's been other challenges, like the desk of you as a PhD student. The desk that you were allocated to was just next to a window. And that means that you've been called at many, many moments in your thesis. But now, right, you're not a PhD student anymore. You are a member of a very select club of PhD holder from KU Leuven. And this is a very warm brotherhood or sisterhood, right? So you'll never be called again. But in case the word from a KU Leuven professor is not enough, I have some actual things that should help you. So that is a compensation from a reimbursement note that has not been accepted by the university. So this is for you. And that's really, hopefully, to keep you warm. Maybe you can use it after your training, or you can use it at other moments. So in case in Japan they don't have central heating. Yes, thank you again. I think you have bright success in front of bright future in front of you. I will be delighted to see what you're gonna do in Japan. I hope we can visit at some point. But thank you.
Okay, I have to untie myself first. I don't have a speech. I just want to say a few words from my heart and kind of echo what Hugues has already said. I think we spent more time together than you and Hugues because we did our master thesis too. I mean, you did your master's thesis. This is going to be engraved on your tombstone, this quote. It's really been a pleasure. You are extremely energetic and motivated, and you have a huge amount of perseverance. And I think the sort of let's say, semi-crisis that you had during your PhD with Gaia not really delivering what we expected. Many PhD students would not have survived that. And you just took the best of what this was that you could salvage. You did amazing work, then you continued doing other stuff. And what Gaia was supposed to deliver, you're going to tell us during your postdoc. So I'm very excited about your future. I'm very proud of you. And I have a small present. So I thought, okay, you're a swimmer. I'm amazed by this, by her ability to do sports like this and then do science. So I thought it has to be something related to the sea. The Dead Sea. I come from Israel, so the Dead Sea is an obvious place. And then we prepared a whole set of Dead Sea products for you, but then it turned out I couldn't take them in the luggage. And so there is one small Dead Sea product here, and the rest is just like cool products, and you let me know if they do any magic. Okay, so congratulations. Yeah.
So I thank you very much both for the very nice words. I also prepared some words myself. I hope I'll get through them without crying, but we'll see about that. So I'll start with you, Tomer. Indeed, as mentioned, you were already my master thesis supervisor, and of course together with Laurent also. And somewhere halfway, I remember we were writing a big application for something which might determine my future, which was an FW PhD application. And I remember we were writing this, and I was following a little bit your scheme, and there was a section of why me. And I just wrote a little bit of 4 lines of like, yeah, and I can do this and this. And then one Friday evening or morning at like 2 a.m. in the morning, Tomer was live editing these documents, and I was still awake because I was afraid, like, this is actually my application. I can't, like, leave him alone in the document, right? And so I stood there. I just was behind my screen. Yes, Tomer, I was watching what you were all doing. And at some point, he started the why me section, and he started writing, and I have expertise in this and this, and I was baffled. I was just amazed by what Tomer, like, my supervisor was writing about me. And not only the written things that you said also during a PhD, you said some of these things as well. And maybe from the outside, it didn't always seem like I appreciate them, but really, I mean, thank you so much. They really meant so much to me. Sorry, I have a little bit of lines. So, Tomer, you're not also understanding, but you're also, I think, very approachable. I feel like you care, you listen, and there is anything I can say to you. Also, like the nice chat we had in Jerusalem, the nice evening dinner. I remember you saved me from a very drunk Israeli guy there, so thank you so much. It's really a shame that we didn't get to spend the whole PhD here in Leuven. I mean, I'm really good for you that you, of course, had the other positions. But so in the end, I think somewhere after 1.5 years or something in PhD, you moved to the Netherlands. But I got the very nice opportunity to visit Amsterdam because of that. Visit some nice scientists in Amsterdam as well, like Natalie and Sylvia. And I feel like every time we meet, I mean, everyone's saying I'm enthusiastic, but I really also feel like you're also so enthusiastic. And you're so like, yeah, let's do this, and so much energy as well. And I think, thank you for all of that. The gifts come later. Dear Hugues, somewhere in the middle of my PhD, a major event was happening. It was the Gaia data release. And I remember, so of course we prepared a lot of time towards this. And on the day itself, I think I just dropped my bags in the office, took my computer, and I stepped myself in your office. We were just sitting there the whole day waiting until noon or something until it would happen. We're sitting there fully stressed. Well, at least I was very nervous at that time. And so it happened. We did it. Unfortunately, not really a lot of results. But we kept on trying. We kept on trying. We kept on trying to find massive stars in this catalog. And I remember I ran out of your office constantly. I went back in. I don't know if I was annoying you. Probably I was, because it was constantly there. I was just programming there. He was just sitting there. We were not chatting. We were just sitting there, me in the professor's office. But really, thank you, because you were really there for me the whole day. Like, we tried to still try. We tried a lot. And I really appreciated that. And not only that time, but as you mentioned, like almost any time, every morning, I was like, hey, Hugues, you have 5 minutes? And really, Hugues already knew it was not going to be 5 minutes. I really still tried to keep it to 5 minutes, but, you know, it was just, I'll keep on trying to get to the 5 minutes, Hugues. And during our conversations, it was not common for you or for me to make a joke. And we laughed so many times. And I really enjoyed all of our conversations so much. And also, Hugues, I never felt like there was anything I couldn't say to you, whether it was some exciting science or whether it was a little bit of a more emotional subject at some point. You would always listen. And I have the feeling, like, actually, like, we really got along with you as well, Thomas. I'm sorry, like, I can't use all the same words, right? And so I also have the feeling that you really care about all your PhD students. At least you always ask, like, oh, how was the swimming competition? And you just, in times of stress, you just came into my office a little bit and say, oh, how are you doing? Oh, just relax. And it's all okay. And I really appreciate all of that. It was amazing learning so many things from both of you. So also, thank you for all of that. And then the final lines, oh, I'm doing great. So I think the three of us saw some science ups and downs, right, in the PhD, but both of you kept supporting me, kept believing in me, and I really can't thank you enough for that. And as I said in my thesis, I really mean it, I could not have wished for better supervisors. And I think that deserves a little appropriate gift.
Thank you.
And then, of course, you can open it. And of course, also to my parents, my family, all my friends, colleagues who are all here, who are rooting for me from online, from behind their screens. Thank you so much for being here, for always being there for me, supporting me. I really could not have done any of this without you. And with that note, I think it's time for the reception.
Super goed gedaan, echt waar.
Also, wait, stop the recording.